Now that we've examined the evidence for and the processes and mechanisms of plate tectonics, we're now going to come in and take a look at some of the particular plate margins in a little bit more detail. Now this video will help you to grasp it. It'll also help you to complete your A3 revision poster as we work our way through this. Okay, let's jump to bookmark number 1, which is the first of our margins, the Mid-Atlantic Ridge. Now I've got a layer on here showing the world ocean base, which will let you see a little bit of that feature. I'm just turning this off so we can see this a little bit more clearly. So what you've got running down here is your mid-ocean ridge. But the ridge is a very, very wide feature. If you remember, we'll just stick the measure tool on here and get an approximate measurement there. Something in the region of 2,500 kilometers wide. A very, very large feature. But in towards the center of this feature, we have another feature running down the middle of it. Can you see this here? So let me turn this layer on, Mid-Atlantic Ridge, so you can see where it is. And that other feature there running down the middle is an important aspect of this. So let's have a look at our revision poster and we'll zoom into this mid-ocean ridge. Here it is here, and we'll have a wee look at what's happening. Now you'll remember from before that this is the asthenosphere here, and the orange and the brown is the lithosphere. The convection current is rising in the asthenosphere. It's bringing heat towards the surface, and as it does so, it makes the lithosphere hotter and more buoyant. It rises up and it stretches and thins it out. And because you have got it rising up here, you'll remember from before that the sides fall away laterally under gravity. So that is what forms your actual mid-ocean ridge itself. But in the center of this ridge, you have got this central rift valley. This is formed because as the lithosphere is bent up, it fractures and faults form. And what basically will happen is that the central block will fall down through some of those blocks, and through some of those faults. So you will get this central rift valley in the middle of it. Now there it is there, the central rift valley. In the middle of that wider ridge. You'll also get a series here of stepped terraces. I'll explain in class in a little bit more detail how they form. So the ridge, the central rift valley, and the stepped terraces. Now the locations of these around the world, you can add these onto your poster. It comes all the way down here through the middle of the Atlantic, around here through the Indian Ocean to the south of Australia, along the south here, and then you have got the East Pacific rise up here towards Mexico. So this massive, longest mountain range chain in the world. Okay, that is your Mid-Atlantic Ridge. Now, let's go to the next bookmark. Let's pop in here to the Indian Ocean. You'll see that in operation. There it is there. There's the Central Rift Valley, and there's the ridge. And the next one that we will go to is up here to the Red Sea. Now, there's something that I want you to see in operation here in the Red Sea. If I zoom out just a little bit, you'll see the context of where we are with this, and zoom back in again. You'll see there a central rift valley. Now, what we have here is a linear sea. Let me turn this off so that we can see the land around it a little bit better now. And I'm going to turn on East Africa Rift. And I want to explain a wee bit about what is happening here. If you went back about 60 million years ago, this Arabian Peninsula here would have been attached to the rest of the continent of Africa. Zoom out just to remind us of where we're at. There's Africa, there's Arabia. But since then, what has begun to happen is that the Arabian Peninsula has begun to split off. So let's have a wee look at this bookmark here. I'll just open this in a new tab so that we can see this more quickly, because this brings us back to the Earth about 60 million years ago. There is Africa, and there you can see the Arabian Peninsula is still attached to the rest of Africa. But the reason why I'm bringing you back here, because I want you to see this part of the British Isles here. There is Greenland and there's North America, and you will see actually about 60 million years ago, the opening up of the North Atlantic is just beginning to happen. And you can see this linear sea here, which is very, very similar to the linear sea that is happening here. So the process here is just starting the creation of what is a very, very narrow sea, the Red Sea at the moment, but could well grow to be something much, much bigger as the North Atlantic did. In fact, if we track this a little bit further down here, we can begin to see linear features here. Anytime there's a linear feature when you're looking at tectonics, it should pique your interest. Let's go in a little bit closer and see what we see in this linear feature. So if I go to this is Ert Ali, right? This is an active shield volcano in the Afar region of Ethiopia. Let's zoom in a little bit closer and see this. It's one of the hottest regions in the world in the Danakil Depression. So let's zoom on in to take a wee look at this volcano. Here it is here. You can see that there are two craters here, and this is one of the few volcanoes in the world that actually has an active lava lake. If you go and stand at the edge of that, you'll actually see a lava lake in there bubbling away. There are not very many volcanoes across the world that are like that. So here we go. Here's to zoom in a little bit closer for Ert Ali, and you can see this. Those are the two craters steaming away. So you get volcanic activity occurring here in this location. Let's zoom out a little bit more. Let's travel a little bit further down. Remember, we spotted a bit of a linear feature happening here. So if we travel a little bit further down, I want to take a look at this region now. We can see here again a linear feature, but these are lakes. So what you're beginning to see here are linear lakes. Now, there are volcanoes here as well. There you go. There's another one. Let's open this and just have a quick look at it. Right. There's another volcano. And of course, let's have a quick zoom in and pay it a little visit. Why not? Because we're here. In this aerial photograph, you can see some of the smoke and the steam appearing from the top of them. So we're still in a volcanic area here. It's tectonically active, and you're starting to have these linear lakes. Now, I hope you can also see here that what you've got is a cliff here, an escarpment, and you've got a central, hold on, a central rift valley. That's interesting. We've seen one of those before, haven't we? Let's click on this and we'll open this in a new tab and we'll have a look. What this shows us here is a computer enhanced version of that. There's those linear lakes occupying the central rift valley. So what we are seeing is volcanic activity and a central rift valley filling with lakes. In fact, if we take a look at this gives us an elevation profile. Again, I'll open this up here. As we run here across Lake Malawi, look, it's a very linear lake. Let's have a look at the topography. We gently rise up to a peak and then a steep slope down to a rift valley, and the same the other side. So what is happening here? Well, what geologists believe is happening here is that there is tectonic activity happening in the east part of Africa, and it's been happening up here and has begun to open up the Red Sea here. And there's some evidence here that there's similar kind of volcanic activity happening along the East African Rift Valley. And if we fast forward 30, 40, 50, 60 million years, we may well find that these linear lakes here have indeed become a linear sea, and we may well find that the Horn of Africa here has split off. So we're beginning to see that process of plate divergence. Well, these are still part of the same plate, but the very, very early stages perhaps of a new plate margin forming here, splitting this apart. And it's the same kind of process that probably went or took place whenever Pangaea was starting to split apart. Okay, so that is our first type of plate margin. That is our constructive plate margin. We see it in the mid-ocean ridges that are happening here. So they're all mid-ocean ridges and coming up here into the Red Sea, but there is some evidence that perhaps we're beginning to get this splitting away here. Okay, let's go to the second of our plate margins, and we're going to take a look here at conservative margins. Okay, so you'll remember from GCSE that a conservative plate margin happens whenever plates are moving alongside each other. What I want to do is to look in here and see precisely and exactly how they form and where. Now, we're back in the middle of the Atlantic again. The blue lines here represent the mid-ocean ridge and the central rift valley. If I just turn that off for a second, there you can see the central rift valley running along here. Pop that back on. But you will also notice that that central rift valley is kind of broken up a little bit. It doesn't run in one single and continuous line. It'll come down here and then boom, that'll shunt over and down here, shunt over and down here, shunt over and down here, and so on. You get this movement, you get this displacement as you move down the center of the Atlantic Ocean. These green lines represent what are called transform faults. They run perpendicular to the central rift valley in the ridge, and they bisect it like that. Now, these transform faults are your conservative plate margins. So my question to you is this, is to try and figure out what the plate movement is in these kinds of areas here. So you've got the plate moving apart here, so it's moving in that direction here, and it's that direction here, that direction here, that direction here. How does that movement produce plates moving alongside each other at the conservative plate margin? Well, let's have a wee look further down here and see if you can figure that out. Here's a bit more of a clue. This is moving here, this is moving here, moving here, moving here. How does that create plates moving alongside each other? Okay, let me reveal these arrows as well and see if that helps you out at all. Right, let me explain this to you and see if you've got this correctly. I've added in a few letters here to see if that's going to help us a little bit. So, we've got this constructive plate margin here with the plates moving apart, constructive plate margin here with the plates moving apart. Now, between A and B, B and C, C and D. Right, let's start off with B and C first of all. Because these plates are moving apart here, because these plates are moving apart here, you can see between B and C, the plates are moving alongside each other in different directions. Between C and D, however, the plates are moving alongside each other in the same direction. Between A and B, the plates are also moving alongside each other in the same direction. But between B and C, you do have them moving alongside in a different direction, and this is exactly what we'd expect at a conservative plate margin. So basically what we're discovering here is that these conservative plate margins are transform faults that bisect the mid-ocean ridges here. Now, what kind of length is that? Let's get a bit of a sense of the scale. Turn this on here. And over to here. So that's, 572 kilometers in length. With that, it's a really, really big scale feature. So these are massive in length. We're not talking about little small faults, big faults here. But they are bisecting across in here the mid-ocean ridges. Now I'm about to turn on a layer here of global earthquakes. Now I wonder, can you think what the pattern will be? Where would you expect most of the earthquakes to be occurring along here? So you need somewhere where the plates are moving in a different direction. You need somewhere where this pressure is building up due to friction that can be released suddenly with the earthquake. So let's turn this on and see where they're found. Oh, look, isn't that a really interesting pattern? They come down here along the mid-ocean ridge a little bit, but look at how many you've got here along these transform faults where the plates are moving in different directions. You can see some along here as well, and it is really quite incredible. If we zoom out and we'll see that these earthquakes are occurring along the mid-ocean ridges, yes, and then the transform fault where they're moving alongside each other. And you can see very much that pattern is taking place. So it really confirms for us that the plates are moving in opposite directions there to produce the earthquakes that are occurring along that transform fault. We're going to take a look at another transform fault, the most famous one in the world, and this is the San Andreas Fault. If we zoom out a little bit just to remind you of where we are with this, in fact I'll zoom out all the way over here and I'll turn these earthquakes off because they get in the way a little bit. This is where we were before in the mid-ocean ridge, and I'm going to come over here to Mexico, and this is the Baja Mexico Peninsula here, and this is the Gulf of Mexico. Now, I wonder, does this look anything at all like somewhere that we have just been in the world? We have got a linear body of water with a constructive margin running down the middle of it. Did that remind you at all of, let's go over here again. Did that remind you of the Red Sea? Well, probably should do, because we've got a very similar process occurring here. A linear sea, and this part of Mexico, Eastern North America or Western North America, sorry, is splitting off from the rest of it. Now, as we have just seen in the ocean there, we have got our mid-ocean ridge, in fact mid-sea ridge in this case, but we have got our transform faults bisecting it. So let's come all the way up here to the top, to the northern part of the Gulf of Mexico, and we pick up our transform fault again, only this transform fault is really long. Comes over the border into North America, and it comes up here, just zoom in, comes past San Diego. There's San Diego. So it comes past San Diego, and it runs all the way through the state of California. This is, of course, there's LA in the way past, this is the San Andreas Fault. We come past San Francisco, there it is. And eventually this comes back out into the sea again, where it joins with the next part of the constructive plate margin, and there is the ridge and the Central Rift Valley again. So let's zoom out just to get a little bit of the context of this. So what we're basically seeing here is a constructive plate margin there, back up there again, connected by, and it probably starts all the way out here, this fault line, this transform fault, which is here your conservative margin, your San Andreas Fault. Now the plates there are moving in opposite directions, so there we get that movement that we saw in the ocean. And let's have a look at what this looks like in the landscape. We'll open this in a new tab. Here we go here, and there it is. The scar running across the landscape where one of the plates is moving in one direction and the other is moving in the other direction. Now, let's turn on the earthquakes again. What pattern of earthquakes are you expecting to see? Where are we earthquakes? Here we are. And you can see the earthquakes running along this. Now, we'll discover as we look at California in a little bit more detail in due course that there are many, many other faults in California as well, which you can see the epicenters of these earthquakes there as well. But here's the San Andreas Fault. Now, I'm very, very glad that there are other faults there as well, because I was not too far away at all from the San Andreas Fault in July 2019. This is down in Redlands. I was in here visiting, and there's the San Andreas Fault. It was just a few kilometers away from the San Andreas Fault when the biggest earthquake in California in 20 years struck. Thankfully not here. Thankfully it was one of the other faults, but we're really very, very close to it at that point. So there is your transform fault. I'll just turn these earthquakes off again. Most of them are features down here in the middle of the oceans, but you can get this really famous one in California. Now, if I turn on this one, plate tectonic margins, oh no, I'll do that a wee bit later, I think. No, in fact, no, we'll just look at this now, because if we look at the key here, the blue is the ridge of the constructive plate margin, but you will see just how much that's bisected by the red of the transform fault of your conservative plate margin. You can see that these central rift valleys and the ridges are bisected a lot by these transform faults in these red running all the way around here. So if we follow all these ridges, you'll see them all the way around here into the South Pacific, up the East Pacific rise. You can see a lot of these transform faults, and where we follow this all the way back up here to the Gulf of California, where we were before, and oh, there we are, the San Andreas Fault coming back out here into this constructive plate margin. So you can see that most of them are on ocean floors, but you do get this one, the San Andreas Fault, forming over land. Okay, so that is in blue our constructive plate margins, in red our destructive plate margins. The next one that we're going to go to here is the first of the converging margins, which is our collision zone. Right, let me turn this off for a moment, and our collision zone that we're going to go into, bookmark here, is number 5, collision zone, which takes us into, where in the world are we? India crashing into Asia, of course. Right, now let's go and have a look at a little bit of evidence that this is a collision zone. And if we turn on the plate boundaries, you can see the boundary is running across here. Turn that back off again. We'll zoom in a little bit closer, and we absolutely have this crumple zone here where India crashed into Asia and is producing these fold mountains. So you can see this ridge of the Himalayas here. In behind it, you've got this upland area of the Tibetan Plateau. So let me turn on this because I want to get a wee bit of a sense of the geology that we have here. In the pinks here, you have got your metamorphic rocks. In green here, you've got your sediments. So I want you to think for a moment why that is exactly the pattern that you would expect. Now, to help you with that, we're going to go back to our revision poster. Here is the collision zone here, and just to remind you of what you would have covered this on this at GCSE. So India has only crashed into Asia relatively recently. It's in the last 50 million years or so. Prior to that, this was India approaching up here to Asia. And you had them separated by this sea. Now, what was happening was that sediment was being eroded off the continents and was building up on the sea floor, and that was being compressed over time to form the seafloor sediments and some of the sedimentary rock. Whenever these two continents finally met and collided, when there was no more oceanic lithosphere or oceanic crust between them, then the seafloor sediments that had been laid down were lifted up and crumpled upwards to form the Himalayas. That's why you can get actually fossils of sea creatures in the world's tallest mountains, because they weren't formed in the world's tallest mountains. They were formed whenever they were laid down as sediments at the bottom of the ocean. Since then, they've crumpled upwards to form these mountains. Now, whenever you exert rock to heat, or in this case pressure, because of the collision, you change the sedimentary rock into metamorphic rock, which brings us back to this. There is your metamorphic rock, and you have your sediments here. It's partly because this is a lowland area and you get a lot of sediments deposited, but this is your metamorphic rock here. Now, let's turn on a slightly more complex map of the lithosphere. So the kind of olive green colors here, if I click on these, it'll tell us the type. It's your metamorphics. So you can see running all the way down this collision zone here, you've got your metamorphics. If we turn that back off again, do you see? There is your mountain range. That's your metamorphic rock that has been formed by the collision. And down here, what have you got? You got, in this case, unconsolidated sediments. You got that just deposited more recently by rivers, but it is sitting on top of the kind of sediments that would have been crumpled upwards to form that rock in that collision zone. So you can just have an explore of that yourself, just to really get a sense of the place in this, and just the sheer, look at all that, the warping and the twisting of those rocks down there as these continents collided together. You get that massive sense of that big collision and that crumple zone that still exists there to this day. Now, if I turn on our plate boundaries, you'll see there's your collision zone there. But you remember what red is? Red's a transform fault, moving alongside each other. Well, it's exactly what you would expect. If India is crashing in that way, this is your collision zone, and as it has crashed into Asia, this is now moving in this direction, this is moving in this direction, so you've got in between them a transform fault. Of course you do. But the main thing of interest here was this collision zone between them. Okay, next up in our poster, we are going to take a look at the destructive plate margins, and there are two types of them. The destructive plate margin, where you get ocean crust meeting ocean crust, and then ocean meeting continental. Let's go back into the GIS and have we look. The next bookmark is going to take us then to Ocean Trench Island Arc. Now we'll come all the way down here to the South Pacific and zoom out to see where we're at here. There is South America, there is Southern Africa, and we're in this little set of islands here known gloriously as the South Sandwich Islands. Now let me turn this off to see what patterns we've got. Dark blue, which means that we've got a trench and we have got islands. Now again, there's your linear pattern, but I'd like you to notice that this linear pattern of islands is parallel to the trench. So I wonder what these islands are formed from. Let's go in and have a look at Montague Island. So Montague Island is a volcanic island which is just sitting here. I'll zoom out a wee bit to get its context, just to the west of the trench. There's the trench, there's Montague Island. So let's zoom in a little bit closer and see if you can get your bearings with this. There's the volcano in the middle of it. I zoom into this distance. I'm going to turn this on, this layer, and we'll get a little bit more detail about it. So Mount Belinda is the volcano right in the middle of that. And in fact, there was a very large and catastrophic eruption here in the past, which has left this large caldera. If I turn that off, hopefully you can just see the edge of that crater. And in the center, a new volcanic cone has built up again at Mount Belinda. So this is a volcanic island. Okay, and now let's zoom on down to some of the others that here. Are these all volcanic islands? Well, yes, they are. And you go in here, you can absolutely see that there is your volcanic island there again. Let's have a look at another one down here. You can see very much your volcano. You can see the crater at the top of that one as well. So what you have is a whole series of volcanic islands with craters in the middle of them that are forming a linear pattern that's running parallel to the trench. Anytime you get this linear pattern, it's suggesting that something's going on. So what has happened here to produce these? Let's go to this little diagram here. And again, we'll go over this in more detail in class, but basically what is happening here is you've got your oceanic lithosphere meeting other oceanic lithosphere. One of them will be colder, older and denser than the other, and it will subduct down into the asthenosphere. But as it subducts down, a lot of the water here that is percolated into the ocean floor, that water that is brought down acts basically as a catalyst to the rock in the asthenosphere. It lowers the melting point of the rock in the asthenosphere. Now, important point to remember here, the asthenosphere is solid and ductile. It'll flow, but it is solid. It is not molten magma. Molten magma is semi-solid. It will flow, but you need to create the magma. How do you create it? Well, you melt the asthenosphere rock here, and you melt it by this process of the seawater coming down, causing the melting point of the asthenosphere to be lowered, creating this partial melting of the asthenosphere, producing magma. Magma is less dense than the surrounding asthenosphere, so it will rise up, form a magma chamber here, and will erupt at the surface over time, building up and up and up and up and up to produce these volcanoes. This is known as hydration melting, and that's what produces the magma, which will erupt to produce these volcanic islands. Now let's go on and have a look then at the other type of destructive plate margin. That's what happens when, no, actually there's one other location that I want us to go and visit, of course, silly me. Right, let's go on and see that. Let's go up here to Ocean Trench Island Arc, up around about this part of the world, right? So here we have our trench again. Here we have our island arc. Now again, look at that, there's a linear pattern, and the islands are parallel to the trench. Let's turn on the plate margins here again, and you can see there's your destructive plate margin, your Ocean Trench Island Arc. Let's go and have a look at one of the islands here. This is Pyre Peak. Zoom out a little bit just to see exactly where we are. There we go. This island chain, by the way, is known as the Aleutian Islands, but we'll come back in here to Pyre Peak because this is absolutely worth exploring. Look at that little island. It's not hidden by snow like the other one was, so you can go in here and have a really close look. There is your crater, and you can totally see the lava flows that have come down from here and have encased the surface. To come down here, you can see the edge of the lava flow coming right down to the side of the island. You can see just how geologically and tectonically active this is, and as the material erupts out, it builds up layer upon layer, building up the height of the island. And there's another volcano over there doing the same thing. And that produces this island. This is part of an island arc, which is again a linear pattern of islands, which is parallel to the plate, or parallel to the trench. Okay, let's go then to this here, which is I'll turn this back on again, plate boundaries. Here we are up towards northwest United States of America, and we're in towards the likes of Seattle at this point in Washington State. And at this point, what we have here is a destructive plate margin. The trench isn't quite as deep there, but you can see the trench. I'll turn that back on. And you have got your mountains here, and you have got some of your volcanoes occurring here as well. So let's go back into the diagram to see what is going to happen here, and we can then go and see it in reality. So in this case, we've got the oceanic lithosphere, which is colder, older, and denser than the continental lithosphere. It's coming down into the asthenosphere. Remember, it is bringing water down with it, and it's leading to that hydration melting of the asthenosphere because it lowers the melting point, leading to partial melting, producing magma. Magma is less dense than the surrounding asthenosphere rock, and it rises up into the surface, forming the magma chamber, and erupts over time to form the volcano. So it's very, very similar to what we've just looked at, only this time you've got oceanic lithosphere meeting continental lithosphere. So let's go in and see if we can find the volcanoes here. There is Seattle. There's the city of Seattle. Right, and you come just down here, and this is one of the most famous volcanoes. Let me turn on this, which shows you the volcanoes layers, and we click on that, and this is Mount Rainier. Okay, so zoom out just a little bit, we'll get a sense of the scale of how far away Mount Rainier is from Seattle, and you're talking about 40 kilometers away. It's very, very close, very visible from the city itself. But that's not the only volcano that you have here. If we come down a little bit, we don't need to go too far, to a volcano that I'm hoping you'll remember from your GCSE days. This is Mount St. Helens, erupted in 1980, and we'll take a wee look at this later when we're looking at volcanic hazards, because you can see here the absolute devastation wrought by this. This is the one where the side of the mountain came away and this lateral blast came out. You can see the crater here. The whole of the mountain top and side was blown away. You can see the devastation from that, and you can see the start of a new volcanic cone beginning to build in the old crater. We zoom out a little bit, we can see the effects of the ash flow and the mud flows that we'll look at, the pyroclastic flows, and you can see all of that devastation of that volcano that erupted in 1980. In fact, if I zoom out a little bit more, you'll see that there are a whole bunch of volcanoes in and around about this area, and because you've got the oceanic lithosphere subducting underneath, the hydration melting is then producing the magma, which rises up and erupts to form these volcanoes. So those are some of your volcanoes in the Cascade region of North America, and we're going to go on to take a look at South America as our last particular example of this. Again, here we have our ocean trench. If I turn this plate margins off here, you'll see it much, much more clearly. There's our ocean trench running down the whole of South America, and you've got your oceanic lithosphere here meeting your continental lithosphere. Only this time, look at how many volcanoes you have got. You've got so many volcanoes forming here. And if we zoom in, you know, pick just any of them at random here. You can go and explore this in the map yourself. You can just see all these many, many volcanoes. There are the craters there. You can see the evidence of the eruption that's come out from that, building up layer upon layer to form the Andes. Look at that one. Look at the radial pattern there of the material that has erupted. Absolutely beautiful. It's the kind of scenery I would love to go and stand in. I'd look at the colours of the landscape. Can you just imagine what it must be like to stand there and look down into that? Now, again, let's get a bit of a sense of the scale with this, shall we? What's the diameter there? So that's 1.5 kilometers across. If you've ever run the 1500 meters, that's the length of that. So you know the distance of that, what it would be like to stand in that barren landscape. It would feel almost like you were visiting the surface of another planet, wouldn't it? You could see the sense of the tectonic activity there of all those volcanoes that are building up the Andes. We zoom out, we see so many of them there because you have got the oceanic lithosphere subducting down in underneath, and you're getting then the hydration melting, leading to partial melting of the rock of the asthenosphere, producing the magma. It is less dense and it rises up to form all of those volcanoes. The last place that we're going to visit here is a volcano just in the northern part of this mountain chain here. I'll zoom out a little bit so that you can see it again, see where we are, and zoom in. This is Nevado del Ruiz. Now, the reason why I'm visiting this is because this is a volcano that we'll look at a little bit later on when we look at the whole issue of management of volcanic hazards. And I just want to touch base with this volcano now so that you can see where this is in the world. We'll touch base with that there and draw back on that later. Okay, so we zoom out and let me turn on this of the world plate boundaries. In fact, let me put this one on the slightly more detailed version and we'll turn on the legend. So what I was hoping that you would get from that is a real good spatial awareness. Now, you will have your map, you'll produce your A3 revision posters just to show you these different patterns of tectonic activity in the different oceans and the different plate margins. You can add more detail on even than I've got there. But you have access to this at any stage where you can go through and have a look at that. You can explore those patterns. So you can see here in the Pacific, the Pacific Ring of Fire, look at how many volcanoes there are around those destructive margins. And you really begin to pick up a pattern of where these features are in the world. The reason for that is I think this is a really good spatial context for you to have anyway, but it also means that let's say you get an exam question about the Southern Atlantic Ocean. You will know from what you've done in your poster, Southern Atlantic Ocean is your constructive plate margin, your mid-Atlantic ridge, and you'll have a sense even before you have to decode anything in the resource itself of what you're likely to find here. If you're given an exam question about the South Sandwich Islands, you will know about those before you even have to decode the question itself. If you're given a question about the Aleutian Islands up here, you will know the ocean trench island arc pattern and so on and so forth. So between this video, exploring that map, that GIS map yourself, and just really going and having a virtual field trip through the Andes, for example, to really increase your spatial awareness of these features, and then use that to produce a really nicely detailed annotated A3 revision poster that's really going to help to develop not just your awareness of some theoretical examples here of plate margins, but the theory of these plate margins deeply contextualized into place.